Its birth began in the shadow of war, with a sketch that could have been forgotten forever. But hidden within this machine were secrets that even the test pilots kept silent about. Why was the first prototype disassembled immediately after assembly? How was the Soviet flying boat simpler and more dangerous than the legendary Catalina? And what structural details were designed for survival in conditions where one wrong move meant the crew's death? Until the very end, we'll uncover facts that they preferred not to speak about openly. August 1942. The world around is shaken by cannon fire, and the fate of the nation is being decided in its heart. The Battle of Stalingrad is raging. It seems there isn't a single spare resource, not a single minute to spare for anything that doesn't immediately benefit the front. In such days, every designer and every factory work for only one goal: to give the army as many ready-to-fly machines as possible, capable of taking off tomorrow. But in Georgy Beryev's design bureau, a concept was born that was too bold for its time. Sketches for a long-range maritime reconnaissance aircraft, designated MDR-10, were laid on the table. At first glance, it was just a set of drawings, neatly drawn lines reflecting a thought about the future. But the project hid an entire philosophy that was ahead of the needs of the day. Beriev envisioned a twin-engine aircraft with a high gull wing, a bulky boat-like fuselage, and twin vertical stabilizers. All of this seemed unusual and even avant-garde. But precisely this configuration could give the Navy what it desperately lacked: range, stability on the water, the capacity for a formidable fuel and payload reserve, and thus the ability to handle tasks that previous single-engine seaplanes couldn't. However, reality was merciless. The country was on the brink, and no leadership could afford to divert effort and materials to a paper project. Every plank and every sheet of duralumin went to mass production. Every available pair of hands was occupied with matters immediately needed by the front. Therefore, despite its potential, the MDR-10 was postponed. In official papers, this was simply called filed away. For many ideas, this phrase meant the end, but not for this concept. Unlike many forgotten projects, Beryev's drawings were preserved as a quiet reserve for the future. Its configuration solutions, its unusual take on the wing and tail shape, its ideas about the capabilities of the flying boat fuselage did not vanish. They seemed to be waiting for their moment to reappear and take shape in metal a few years later, when the country would catch its breath after the war. Thus, in the darkest year of the war, when everyone's attention was fixed on the front line, a project that was destined to change the face of Soviet naval aviation was born in the shadow of the drafting tables. No one could know then that the history of a machine that would become one of the symbols of the post-war era would begin with these unnoticed sketches. By early 1943, the war at sea had clearly demonstrated the weaknesses of the existing naval aircraft. The old single-engine MBR-2s, recently considered the workhorse, were rapidly losing value. Their range was insufficient to cover vast expanses. Their payload was minimal, and their capabilities for reconnaissance and supporting naval operations were limited by outdated technology. The Navy needed a completely different weapon, a machine capable of replacing several aircraft types at once and taking on a wide range of tasks. The experience of combat clearly proved that heavy flying boats were indispensable. An aircraft was needed that could patrol the sea for days, detect enemy submarines, transport cargo and personnel, conduct reconnaissance and coastal photography, and, if necessary, operate as a full-fledged maritime bomber or lay mines. The old equipment could no longer withstand the pressure of new requirements. The Navy operating in the Black and Northern Seas felt this most acutely. At this moment, the People's Commissar of the Navy, Admiral Nikolai Kuznetsov, spoke the decisive word. He sent a request to the People's Commissariat of the aviation industry, clearly and firmly stating, the country needed a long-range heavy flying boat. This request coincided with the understanding that a new stage was beginning in the world of aviation, where versatility and range were becoming the main characteristics. The response was quick. The People's Commissar of the aviation industry, Alexei Shakharin, authorized the development of such a machine and issued a technical assignment that compiled all the necessary characteristics for the future giant of naval aviation. It was here that the project, the once postponed MDR-10 sketch, was remembered. It already contained the solutions that perfectly matched the new requirements, and the time had come to breathe life into them. Following the official request from the Navy and the issuance of the technical assignment, the forgotten sketch provided a new impetus. Admiral Kuznetsov's appeal and Commissar Sakharin's sanction pulled the project out of the archive drawer not for admiration, but for real work. Beriev returned to his drawings, revised the configuration, reinforced the ideas, and gave them a new name, LL-143. On paper, the machine no longer looked like a vague reminiscence. It had gained specificity, design solutions, and the real technical parameters needed by the fleet. Work started quickly and practically. First, a wooden mock-up appeared, the working model that allowed for examination not only of the shape, but also the landing characteristics, placement of compartments, and floats. The mock-up revealed everything that needed to be seen. In early 1944, the project was approved to move to the practical stage. This meant one thing: it was time to prepare for production. On April 14, 1944, the Krasnoyarsk Aviation Plant began construction of the prototype. The factory, which had just returned to peacetime work after evacuation and struggling with material shortages, took on a task whose scale exceeded the usual production line: to build a flying boat with a bulky fuselage, a complex wing center section, and underwing floats. The new aircraft's features began to appear in the workshops: large frames, long stringers, the framework of the boat section. All this required precision and time, but even then, it was clear that the idea was moving from paper to reality. The revival of the old concept under a new index was not just a technical act. It was a statement that the Navy would receive a tool capable of closing several gaps in naval aviation at once. And although the builders faced difficulties, the first spark of the prototype's creation had already been ignited in the factory workshops, emphasizing that the project, once postponed due to the pressing needs of the front, had re-entered life, now with a clear plan, resources, and the will to see the concept take to the wings and the water. The construction of the new aircraft, which began in Krasnoyarsk, proved to be a test no less demanding than the war itself. The factory, overloaded with orders and suffering from a lack of production facilities, took 13 months to complete the work. Every stage was difficult. Timber and metal arrived with interruptions, tools wore out faster than they could be replaced, and the workforce was exhausted by the war years. Yet, by May 1945, the prototype was ready. The end of the war coincided with the completion of assembly. It seemed the machine could immediately head for test flights, but a new phase of complications awaited. The aircraft had to be disassembled into components, loaded onto railway platforms, and transported to Taganrog. This was where the Beriev Design Bureau was returning after the evacuation, and it was there that flight tests were planned. The transport itself was symbolic. The project, which had survived the difficult years, was now heading to the place where it was supposed to show what it was capable of. The reassembly in Taganrog took another 2 months. Careful tuning, checking every unit and assembly, preparation for the first takeoff. All of this took time, but brought the moment of truth closer. On September 6th, the prototype designated LL-143 took to the air for the first time. At the controls was test pilot Nikolai Kotyakov, with flight mechanic Dmitry Chernetsky beside him. The machine emerged from the water, lifted off the surface, and confidently began to climb. The flight was a success, proving that Beriev's concept was viable not just on paper. That autumn, while the Sea of Azov remained ice-free, the aircraft made 10 more flights. These tests allowed designers and pilots to gather initial feedback on the machine's behavior, noting its stability, predictability in handling, and good response to pilot input. The LL-143 showed itself not as a raw experimental design, but as a full-fledged step toward a future production machine capable of becoming the eyes and weapon of the Navy. In the spring of 1946, when the ice cleared and the water area was again open for flights, the tests resumed. The LL-143 returned to the water, and every flight added confidence that the machine was a success. Test pilots noted the ease of control. Piloting proved to be less strenuous than foreign counterparts. The American Catalina, the famous flying boat already in service with the Soviet Navy, was a particular point of comparison. Unlike it, the new Beriev machine required less physical effort. and gave the pilot more comfort during long-duration flights. The commission carefully recorded all characteristics: how the aircraft accelerated on the water, how it transitioned to planing, and how it behaved in the air during turbulence and strong crosswinds. Every report was full of positive reviews. It seemed the goal had been reached. The Navy was getting a versatile aircraft capable of performing reconnaissance, patrol, and combat missions. But this high evaluation also revealed new requirements. The Soviet leadership understood that years of national reconstruction lay ahead, and military equipment had to not only meet the present day's demands, but also maintain relevance in the future. The Commission recommended reinforcing the armament so the machine could confidently counter aerial threats, and also replacing the engines with more powerful ones. The A-70 engines used proved reliable, but their capabilities were no longer sufficient for the tasks envisioned for the prospective naval aircraft. This was not a redesign for formality's sake, but a strategic move. If the new machine was to serve for decades, it had to be on par with the best world models. And so, after the completion of the test cycle, it became clear that the next stage was modernization, which would transform the successful prototype into a full-fledged combat aircraft worthy of series production. The aircraft, already tested on water and in the air, needed a crucial improvement, and the design bureau acted without delay. Engineers replaced the former engines with more powerful units, the A-73 18-cylinder twin-row radial piston engines, each developing 2,400 horsepower. This wasn't a simple upgrade for a higher number. The new engines provided different behavior during the takeoff run, different grip on the waves, increased cruising range, and allowed for sustained cruising speeds with a greater load. The Soviet flying boat gained what is known as a margin of safety. Now, it could not only patrol longer, but also carry heavier armament without losing controllability. Simultaneously, the defensive section was reinforced. All turrets and machine gun installations were modified, ammunition loads were revised, and the armor and crew compartment protection were optimized for the combat conditions of naval operations. These changes were not cosmetic. They addressed the new concept of the machine's multifunctional application, where a single platform could handle reconnaissance, escort, and direct strike tasks. While the engineering solutions seemed simple in formula, their combination created real tactical flexibility. The renaming was a formal but important step. The improved aircraft was assigned the index Be-6 in recognition of Georgy Mikhailovich Beryev's authorship and contribution. The name confirmed not only the technical changes, but also the idea of continuity. From a sketch shelved during the hardest year, a combat-ready flying boat emerged, ready for service in a new world. In practice, this meant that the project, which began as an echo of a dream, had turned into real wings and metal, gaining the solidity and presence that makes equipment noticeable on the naval horizon. Step by step, the LL-143 ceased to be just a prototype and became a machine capable of taking its place in the ranks. The increased power of the propulsion system, reinforced armament, and modified platform made it not just a response to the challenges of the war, but a tool for the ocean policy and defense of that era. A machine remembered not only for its technical solutions, but also for its ability to carry out missions where reliability and versatility were required. The Be-6 fuselage was constructed as a boat, not an imitation, but a true carrier in water and air, where every detail served a dual function. The frame consisted of a set of frames, spanhouts, and stringers, forming the trough-shaped bottom and sides. There were 44 frames. Some of them served as reinforced supports for large units and gun mounts. The outer skin was glued and riveted to form a rigid box structure in the nose and midsection of the hull, and reinforced panels were provided in the stern area for attaching the detachable tail section. Water tightness was achieved not only by hermetic bulkheads, but also by a system for sealing gaps, drainage pipelines, and a well-thought-out drain system in the recesses where water collected during maneuvers and pitching. The flying boat's behavior on the water was ensured by a carefully calculated hull-bottom profile. The smooth contour, with a pronounced step, allowed for a quick transition to planing during the takeoff run, reducing drag with the waves. The keel and chines of the bottom had reinforced overlays for protection during landings in harsh waves, and longitudinal stringers along the sides distributed the impact loads from the waves along the entire length of the hull. A water rudder, pneumatically actuated and synchronized with the directional rudders, was used for maneuvering at anchor and towing. This solution ensured precise steering at low speeds and reduced the load on mechanics during towing. The wing was essentially a box-type structure with two main spars. The center section supported the engine cowlings and the float attachment points, so the structure could withstand significant concentrated loads. The outer panels were detachable for ease of transport and repair. The leading edges and wingtips were attached with bolted joints and seals, and additional splines were used at the connection points for precise alignment. The flaps were divided into several sections and had a large maximum deflection angle, ensuring a short takeoff run and a soft landing with a full load. The slotted ailerons had axial compensation and mass balancing to eliminate vibrations and facilitate the operation of the control surfaces during longitudinal and lateral maneuvers. The underwing floats were self-contained, two-step shells with internal compartmentation. Each section had its own water drainage system and attachments designed for impact loads during hard landings. The floats were suspended on struts that served as fairings, reducing hydrodynamic drag and protecting the attachment elements from corrosion and mechanical damage. To prevent nosing under in rough seas, the nose section of the floats had a positive angle of incidence. This allowed the contact point with the wave to be shifted, reducing the risk of a pitchover moment during takeoff. The tail unit, a twin-fin design calculated to maintain controllability in case of a single engine failure, had its own damping and trimming system. The horizontal stabilizer, with a pronounced V-angle, ensured lateral stability, and end plate fins with directional rudders were installed at the tips, further supporting efficiency in the slipstream of the propellers. The elevators and directional rudders were equipped with aerodynamic compensation and spring servo boosters, which reduced the forces transmitted to the pilot's controls and lessened crew fatigue during long patrols. Power elements and units were positioned with serviceability in mind. The engines were installed in cowlings with large removable flaps that, when opened, turned into working platforms for maintenance personnel. Access to fuel manifolds, filters, and pumps was provided through hatches in the center section of the wing and the fuselage. The fuel system included several tanks with booster pumps and manual shutoff valves, and the fuel and pipeline routing was designed to allow the isolation of a damaged section without a complete shutdown of the power system. Materials and anti-corrosion protection were a separate chapter of engineering thought. The hull and wings were primarily made of aluminum alloys with localized steel reinforcements in areas of high stress. All external joints were treated with sealants, and internal cavities had a coating to prevent electrochemical corrosion during operation in salt water. This combination of structural techniques made the Be-6 not only a strong, but also a survivable platform in the harsh marine environment, where every part had to withstand a combination of shock, vibration, and corrosive loads while remaining accessible for repair and maintenance. All the equipment aboard the Be-6 was assembled not for show, but to make the aircraft a versatile tool of the sea, simultaneously the eyes, arm, and shield of the Navy. The heart of the machine consisted of two AH-73 18-cylinder radial engines, each developing 2,400 horsepower. Their reliability and power reserve allowed for sustained cruising speeds with a large payload, and provided the necessary dynamics for takeoff in rough seas. The drive rotated four-bladed variable pitch propellers, which gave pilots an important set of tools for economical flight and maneuvers in difficult conditions. The onboard electronics made the Be-6 an independent reconnaissance unit. The PSBN-M search radar allowed objects on the water to be detected long before visual sight. The RV-2 radio altimeter ensured safe flight at low altitudes, and the Magnii and Beret identification systems reduced the risk of errors in multi-layered situations. VHF communication, radio stations, and an automatic radio compass ensured long-duration communication and correct navigation. In conjunction with the gyromagnetic compass, induction compass, and AP5 autopilot, the crew could fly long routes with minimal fatigue. The armament was a logical extension of the concept of versatility. The Be-6 could be used as a reconnaissance aircraft, transporter, and strike platform. The external hardpoints allowed it to carry up to 16 Sexc 100 kd bombs or 8 Is 250 kg bombs, and the sides provided for the installation of AV-type aerial torpedoes, with indices corresponding to the naval models of the time. For combating surface targets, the capability to lay naval mines, including the AMD 500 model, was provided. The defensive armament consisted of several automatic installations, with NR-23 cannons located in the nose, dorsal, and tail turrets, offering a chance to repel enemy attacks during combat sorties. The combination of equipment and weaponry transformed the machine into a submarine hunter. Radar and photographic equipment allowed for the detection of surfaced wakes, and the suspended torpedoes and depth charges made immediate engagement of the detected target possible. At a practical level, such integration meant that one sortie could solve multiple tasks: reconnoiter an area, transmit coordinates to ships, attack a detected object, and, if necessary, evacuate cargo or personnel. The Be-6 was born at the intersection of engineering boldness and the practical demands of the Navy. A machine in which the power plant, radio equipment, and armament were not a collection of separate units, but a folded mechanism for life at sea. Its appearance is an example of how a shelved sketch, carefully preserved in the shadows, was able to grow into a full-fledged symbol of an era, not just because the design was good, but because it met the demands of the time, unifying functions and giving the Navy a new tool for controlling vast expanses and defending state interests.